Now that we know a little bit about differential equations and slope fields, we can use those ideas we've learned to get a better picture of what a function looks like given its differential equation. One way to do that is use something called Euler's method. Euler's method uses a differential equation like the one here and the slope field like the one here, and actually the slope field is not necessary, but it uses this differential equation to get an idea of what the function might look like without having to do much calculus. We've already used the slope field to draw a picture. Say we are given an initial condition like this point here at 0, 0. We can get an idea of what the function will look like just drawing it by hand and kind of following the slope segments. This is not a very accurate method, but it can at least give us an idea of what the function is going to look like. We can do something a little bit more accurate analytically by following Euler's method. At the heart of Euler's method is the fact that the derivative is approximately equal to delta y over delta x. So let's just remind ourselves what this means. Dy over dx, remember these differentials dy and dx are infinitesimally small increments in y and x, so small that we can't see those changes. And delta y over delta x, those are measurable changes in y and x, and we find those by subtracting the differences. And when delta x in particular is very small, and therefore delta y is going to be small also, we get a close approximation to the derivative by finding the slope of secant lines. Well, we can solve this approximation for delta y, and we get an equation that looks like this. Delta y is approximately equal to the derivative times delta x. And this equation right here is going to allow us to get a really good picture of what a function is going to look like and to approximate values on the function that are away from our initial condition. We're going to start at 0, 0 here, and we're going to see what the function is going to look like as we move away from 0, 0. In this particular example, since the derivative is equal to x plus y, given by this differential equation, we can plug that in for dy dx, but we also need to choose a delta x. Remember, when we choose smaller delta x's, this approximation gets closer, so we want to choose something as small as possible but manageable. Usually that delta x will be chosen for you. In this case, since our slope field is marked off by fourths, we'll choose a delta x for 1/4 just to stay consistent with the slope field. So in this example then, we're going to have delta y is approximately equal to x plus y, that comes from our differential equation, times 1/4, that comes from our delta x that we're going to use. Now, since we're starting at 0, 0, this equation right here will tell us how to get another point that will be close to our function. Again, this is an approximation, and essentially what we're doing here is a linear approximation, but we're going to do it over and over again. So we're going to start at 0, 0, and we're going to move to a new point. The x value is going to increase by delta x. That's 1/4. That's something that's never going to change while we're doing this process. So we're going to take the x value and add on 1/4, and we get 1/4. And to figure out what the change in y is going to be, we're going to use that formula. And we put 0 in for x and y here. Our delta x is still 1/4, and so we're going to get a change in y of 0. Since y changes by 0 and starts at 0, then our new y value is going to be 0. What we have here now is a point that is on the linear approximation of our function. Again, we don't know what the function looks like. That's what we're trying to get here. So we're going to plot that point, and we'll draw a segment connecting the initial point to that second point. Now, this is a linear approximation for our function. And what we're going to do now, since we've moved along in our slope field, we're going to find a new slope at that new point. So we can find our next point by changing delta x by 1/4 again. If we increase 1/4 by 1/4, we get to 1/2. And then we can figure out what y is going to change by using our formula again. Now, since we're at the new point, we have a new slope. Our slope is going to be 1/4 plus 0, and we'll multiply that by our delta x of 1/4, and now our y is going to change by 1/16. Since our y started at 0 and increases by 1/16, our new y value is going to be 1/16, and this gives us another new point. This new point now is a closer approximation than we would get if we just use the linear approximation at a with a step of 1/2. Doing the process again, we can move from 1/2 to 1/16 to 3/4 13/64 by using the same process. That's going to be a point just below 1/4, and we get another point. And we can do this over and over and over again, and we can get, again, a picture that's going to give us close to what the function is, but not exactly, because, again, we're using approximations. Moving to the right from our initial condition at 0, 0, we get a string of segments that looks something like this by using the slope at each point to get to the next point, moving by delta x each time. And this, as you can see, follows our slope field fairly consistently, and should be a pretty close approximation for our function. We could do the same thing moving to the left also, just using a negative delta x value, and we would get an idea of what the function looks like there. To see how accurate this is for this particular example, I'll go ahead and superimpose the actual function that would solve this differential equation. And we can see, especially here close to the initial condition, we stay fairly close to the function. The difference between our value for Euler's method and the function are not far off. As we get further and further away, just like any other approximation, we're going to lose some accuracy there. So here's the basic idea for Euler's method. We're going to start at some initial condition. We'll use the differential equation to find the slope at that point. And so then we'll increase delta x by some set value, and we'll increase delta y, or we'll increase y by delta y, where delta y is given by the derivative times delta x. Remember, this is our solution for Euler's method right here. However, in actuality, this is going to be approximately equal to that. And then we'll just repeat that process as many times as we need to get to the value we want. So for example, if we want to approximate the value of a function at 1, and we're starting at 0, we might use 4 steps with a delta x of 1/4. Or we could use 8 steps with a delta x of 8, and that would be our choice. The smaller delta x is, the more accurate our answer is going to be. Just a quick look at the picture. If we do use a delta x that's negative here and move to the left, we already saw the right half of this function, as well as the right half of our result using Euler's method. The left half is going to be a little bit more accurate, mostly because of the nature of our differential equation that we used, and we can see that this is going to be an asymptotic function here.